Hello everyone, welcome to this lecture. In the previous lecture we studied what are FRF estimates and what is coherence function. In this lecture we are going to study the test planning required for FRF measurement. It requires several decisions to be made related to how the measurements are taken and what measurements are taken, and we are going to look at all that. So the topic today is test planning for FRF measurement. A brief outline of the lecture is as follows. First we are going to look at the choice of boundary conditions for FRF measurement. Then we will look at what should be the frequency range for FRF measurement. Then we will look at the number of measurement points, right, on the structure at which FRF should be measured. Then we will also see what are the FRFs that should be measured at these points, right, and in that context we will talk about what is a roving hammer test and what is a roving accelerometer test. After that we will also look at what should be the choice of the response and the force transducer location for roving hammer and roving accelerometer test respectively. Then we will look at the choice of time and frequency domain parameters for FRF measurement and how other parameters of these two domains they are related by these choices. And then at the end we will talk briefly about how the calibration of the measurement system can be done. So the first point we are going to talk today is the choice of boundary conditions for model testing. So choice of boundary conditions for model testing. Okay. So one thing we should note is that the boundary condition, it affects the system's natural frequency, right. Its model is affected by boundary condition. So one example of that could be that if we have say cantilever beam like this, right, of certain geometry and material, so it has certain natural frequencies. But if this same beam with the same geometry and material is supported on simple supports, right. So same beam is simply supported in this manner, then the natural frequencies of the system becomes different, right. The natural frequency of the beam changes, and if in fact it is say freely supported, means it does not have any constraint to move, then under this condition again the natural frequencies would be different. So this simple example clearly demonstrates that the boundary conditions affect the natural frequencies of the system. So now what should be the boundary conditions for model testing? The choice of that depends on the purpose for which the model test results are supposed to be used, right. So what is the objective of the those model testing, the results we are going to get from that, what is going to be the application of that, that basically determines the choice of boundary condition. So therefore the choice of boundary conditions, so that we can abbreviate as BCs, depend upon the purpose for which the model test results are to be used. So one type of boundary condition under which the testing can be done is testing under actual boundary conditions. So testing under actual boundary conditions. So in many cases, the purpose of the model test is to determine the system's natural frequencies, okay, so that the resonant operation of the system, right, or the structure can be avoided. So for achieving this, we need to have an accurate knowledge of the system's natural frequencies, because then only we can ensure that the excitation frequencies, they do not coincide with the system's natural frequencies, so that the resonance can be avoided. So therefore, to obtain the accurate characteristics of the system, accurate natural frequency of the system, we need to test the system with the under the actual boundary conditions, the conditions under which the system operates, right, during operation. So, we need to test the system with the actual boundary conditions, because if that is not done, then the system's natural frequencies cannot be determined accurately, right, because the change in boundary conditions would affect the results. So, therefore, testing under actual boundary conditions should be done when the knowledge of systems natural frequencies is required. For example, to avoid resonant operation of the system. So, that could be one inspiration to obtain the system's natural frequency. Now, this testing under actual boundary conditions, it can be done in two ways, right. One could be in situ testing. There are two options. So, we can have in situ test, right, which means that we test the system when under the actual operating conditions, right. In field we may test the system wherever it is installed and wherever it is being used. So, in situ testing may be done. So, automatically all the actual boundary conditions are taken care of during testing, and the estimate of natural frequencies that result from the model test that are supposed to reflect the natural frequencies of the system with the true or the actual boundary conditions, right. The other possibility is to simulate the actual boundary conditions in a laboratory test, right. So, we can also do or simulate the actual boundary conditions in a laboratory test. So, for this purpose the system or the structure to be tested needs to be brought to the laboratory, and then we need to simulate the boundary conditions under which the system is supposed to operate, right. So, then we can test the system and then determine the system natural frequencies. But obviously, the accuracy of the results that are obtained, they depend on the accuracy with which the simulation of the actual boundary conditions can be carried out in the laboratory. The other boundary conditions under which the model testing is done is they are free and fixed boundary conditions. Okay. So, one of the other important application of model test result is in validation and, if necessary, updating of finite element and other numerical models, right. So, that is another important application of model test results. So, another application of model test results is in the validation and, if necessary, updating of a finite element or numerical models, right, of the given system, right. So, in many cases the validation of the complete system, right, is preceded by validation of its components and subassemblies. So, idea is that we first validate the component and subassemblies by performing model test on individual components and subassemblies, and then assemble those validated component and subassembly models in order to obtain the system model, and then perform the next level of validation, right, that is the validation of the whole system model. So, in such cases, therefore, the objective is to first validate the component models or subassembly models. So, for such cases the component is validated under isolated condition, right, from the assembly. So, component isolated from the assembly is validated, and then the question arises that under what boundary conditions the component should be tested, under what conditions the model testing of the component should be done. It is seen that the free and fixed boundary conditions can be easily incorporated in the finite element model, right, and therefore the model testing therefore can also be done under the free or fixed boundary condition, so that the comparison of the result becomes easier, so that the boundary condition would no longer be a source of discrepancy between the results of the two models, between the results of the FE model and the experiment. So, therefore, free and fixed boundary conditions are used for component level or subassembly validation of the models. So, free and fixed boundary conditions are used for model testing of components and sub assemblies of a system to validate their models. That is the models of the component and subassemblies. So let us first of all talk about what is free boundary condition. So the free boundary condition means that there is no constraint on the structure or the system, right, and therefore it is free to move in any direction. So a body in space, right, can have 6 independent motions, 3 translations and 3 rotations. Okay, so free boundary conditions refers to no constraint. Okay, no constraint to its motion in space. Okay, and then under such condition there can be 3 translations and 3 rotations of the body or the system, right, and therefore these motions are motions where the system or the body does not undergo any strain or deformation, right, and it moves like rigid body, and therefore these modes or these motions, that is 3 translations and 3 rotations, which are independent motions of the body in space, they are referred as rigid body modes. Okay, so they are basically referred as rigid body modes. Okay, because these motions do not produce any deformation or strain in the body. Okay, and because in these motions there are no elastic forces which resist the motion of the body, because body is free. So there are no external elastic forces which are acting on the body, and hence the natural frequency of motion in these modes is 0. Okay, so the natural frequency of rigid body modes is 0. Okay, and 0 when there is a truly free boundary condition. So the question arises, is it possible to realize this true free boundary condition for testing? So in reality the body would need some support in order to support the gravity force, right. So some kind of support needs to be given. So in practice what is done is that body is supported on soft supports. Okay, So, it could be like, for example, soft foam on which the body can be placed, and or it could be suspended from ceiling, which is rigid, using soft elastic or rubber bands. Okay. So, therefore, in practice the free boundary condition is approximated by supporting the body with soft supports, correct. So, for example, we can use like foam supporting it on a foam or suspending it from a rigid ceiling using soft elastic or rubber bands. So, as an example, let us say we have this car body like this, okay, and so like this. So, and let us support it using soft elastic bands like this. So, we can have one band here going like this, and we can have another band here like this, right. And then we can mount a accelerometers at suitable location like this, right, measure the response, and then we can maybe use a hammer to apply the force like this, right, and then measure the force signal and then measure the FRF. But we should note that this is not completely free support, because there is some elastic force that is being applied by the soft supports, right, and because of that the natural frequency of the rigid body modes no longer remains 0, it is more than 0, right. So, the natural frequency of rigid body modes no longer are 0, right, but it is more than 0. So, then what principle should be used to choose the stiffness of these supports, right. So, what is desired is that the flexible modes, the natural frequency of the flexible or the strain modes of the body, they should be very high as compared to the rigid body mode natural frequencies. So, a simple thumb rule is that the natural frequencies of the strain or flexible modes should be like more than 10 times the natural frequencies of the rigid body modes, and therefore, the stiffness of the supports which are being used for simulating the free boundary condition should be such that the natural frequency of the rigid body modes is very small. So, when we ensure that the natural frequencies of strain modes is sufficiently high as compared to rigid body mode natural frequencies, then the natural frequency estimates we get, they would be very good estimates of the natural frequencies of the body under true free boundary condition, right. So, the natural frequencies if are represented by omega n, right, of the rigid body modes right, it must be much smaller than the natural frequencies of the the flexible modes. So, the other boundary condition under which the component of subassembly can be tested is fixed boundary condition. So, in the fixed boundary condition, some degrees of freedom of the body, they are completely constrained, so that the rigid body motions, right, of the body is no rigid body motions are possible. So, some degrees of freedom of the body are fixed so that no rigid body motion is possible. So, these fixed boundary conditions are difficult to realize because it is not that easy to design setup where the degrees of freedom which are to be fixed are actually being completely fixed. There may be small amount of compliance or some amount of flexibility there, right, because of the finite stiffnesses of the the components which are used to make the fixed support, right. The clamps, they may have a finite stiffness. So, it is not very easy to basically force fixed boundary conditions. So, that is why it is relatively easier to simulate the free boundary condition by using very soft supports, and that is why the component or subassembly model tests are generally done with free boundary conditions. So, the fixed boundary conditions are difficult to achieve. So, the next now issue we are going to discuss as part of the test planning is that what should be the frequency range of measurement. So, frequency range of measurement. So, the frequency range of measurement should be the frequency in which we want to study the dynamic response of the structure, right. So, it should be the frequency range in which the dynamic response is to be studied. Okay, we want to find dynamic response in that range, that should be the frequency range. Now, what determines the frequency range of dynamic response? The dynamic response depends upon the excitation forces or the dynamic forces acting, and that is why the frequency range of measurement then can be fixed based on the frequency range of excitation. So, what is the frequency range of the excitation or dynamic forces acting on the system? So, another issue that we need to decide is what are the measurement points, right. The choice of measurement points. So, the measurement points depend upon again what is the purpose of the model test. If the objective of the model test is just to determine the natural frequencies and damping factors of various modes, right. If that is the objective, to have an estimate of the natural frequencies and damping factors, then that can be done with a few number of FRFs. So, we can measure FRFs at some few number of points, and then the analysis of that can reveal the information about the natural frequencies and damping factors. Okay. So, if the objective is to have an estimate of natural frequencies omega n's and damping factors of the modes. So, this can be done using measurement of few FRFs, right, can be done using few measured FRFs. But if the objective of the model test is to obtain the model of the system, right, for a given frequency range, Then we also require information about the mode shapes of the system in addition to the nature frequency and damping factors. Okay. So, that requires measurement at many more points on the structure, so that the mode shapes can be accurately represented. So, if the objective is to identify a model of the system, right, then mode shapes also need to be identified. Number of measurement points should be enough so that spatial aliasing of the mode shapes is avoided. So, what is spatial aliasing? Spatial aliasing occurs if insufficient number of points are used to describe geometry, right, because the mode shape is like a geometric shape. So, if sufficient number of points are not used, then the description will not represent the mode shape correctly, it will be a misrepresentation. A mode shape which is having a complicated shape may be misrepresented by a simpler looking shape. So, therefore, we should have sufficient number of points, sufficient number of measurements, because number of measurement points would determine the number of elements in the each mode shape vector, right, and that number should be enough to describe that mode shape accurately. So, then of course, the mode shape becomes known only when we have the model test results. So, then how one can decide the number of measurement points in the absence of information of the mode shapes? One possibility lies in using any existing numerical model, finite element model or analytical model of that system. If that is available, then we will have some idea of the mode shapes, and then from that we can probably decide that how many measurement points should be taken for measurements. Another issue is that what FRFs at this point should be measured, right. So, FRFs to be measured at test points. So, what FRF should be measured? So, in structures, made up of beams, plates and shells, the relevant DOFs are translational DOFs, and rotational DOFs, correct. So, the translational DOFs present a displacement in the transverse direction at any point on the structure, right, and the rotational DOFs are the slopes at those points. So, now the translational DOFs can be easily measured, but there are no very reliable methods which are available for rotational DOF measurements, right. So, they cannot be so easily measured, and that is why often in model testing we generally measured only the translational DOFs, right. So, this is one point that is of relevance in structures where or systems where the system or structure consists of beams, plates or shells, right. So, these are the DOFs which are generally measured, while these DOFs are generally not measured, right. Another decision that needs to be made, that let us say we have n number of test points, right, and then now should we measure the full FRF matrix corresponding to n test points, right, should we measure the full FRF matrix. So, do we need to measure the full FRF matrix, correct, because if there are n tens points, so we have n by n FRF matrix corresponding to those test points. So, to answer this question, let us look at FRF of a multi-degree of freedom system. So, for a system, let us say with structural damping, the frequency response function alpha j k is given by r varying from 1 to n. Let us say if there are n modes, then we have phi j r phi k r upon omega r square minus omega square plus I eta r omega r square, right. So, this is the frequency response function alpha j k, and what we observe from here. So, we see that in this FRF we have information about all the natural frequencies of the structure, right, because we have omega r is the natural frequency. So, r varying from 1 to n. So, all the natural frequencies affect this FRF. Similarly, if you look at the damping factor eta r, so again all the damping factors affect this FRF. So, it means that this FRF contains information about all the natural frequencies, all the n modes natural frequencies, and the damping factor of all the n modes. And we also have information about phi j r into phi k r. So, it means this FRF also contains information about the product of the jth and kth element of all the mode shapes. Okay. So, this contains information about all natural frequencies, all damping factors, and product of jth and kth elements of all mode shapes, right. And now if we let us say measure the FRFs alpha j k such that k varies from 1 to up to n. Let us say we measure all these FRFs, right. So, these are n FRFs. So, these FRFs then would contain information about all the elements of all the mode shapes, correct. So, this will contain information about all the elements of all the mode shapes, that is all the n mode shapes. So, this means that if we measure these FRFs alpha j k with k varying from 1 to n, then essentially we are measuring the one row of the FRF matrix, because we are fixing the jth coordinate, which is the response degrees of freedom, and then we are applying excitation at k varying from 1 to n. So, that would lead to measurement of one row of the FRF matrix. So, let us now write the FRF matrix here, alpha as alpha 1 1, alpha 1 2 going up to alpha 1 n, right. Then we have alpha j 1, alpha j 2 going up to alpha j n, and then we have alpha n 1, alpha n 2 going up to alpha n n. So, this is the FRF matrix of order n by n. So, when we measure alpha j k with k varying from 1 to n, then essentially we are measuring this row of the FRF matrix, the jth row. That is nothing but the jth row of the FRF matrix. And when we measure this row, what essentially we are doing, the response DOF is fixed at jth point or DOF, right. That response DOF is fixed. So, we are taking measurement or of response at always at jth point, and the excitation DOF is varied, right, from 1 to n. Okay. Now this particular way of applying excitation can be easily carried out using impact hammer, right, because impact hammer to apply excitation at different points, we just need to move the hammer from one point to the other, right, and therefore measurement of this one row of the FRF matrix can be easily accomplished by using an impact hammer. And that is why this strategy in which the response DOF is fixed and the excitation DOF is varied to measure different FRFs is referred as a roving hammer test. Therefore, this is referred as a roving hammer test. Okay. So, the hammer is moved or rolled from one point to the next and to the last point. An alternative is to now measure all the FRFs, right, alpha jk by varying the jth coordinate from 1 to up to n, right, and all these FRFs which result, they basically represent one column of the FRF, represents kth column of the FRF matrix, correct. So, if you show the FRF matrix here, then and write down these things alpha 1 1, alpha 1 2 up to alpha 1 n, right, and also include, let us say, alpha 1 k here, then we have alpha 2 1, alpha 2 2, alpha 2 k, alpha 2 n, and going up to alpha n 1, alpha n 2, alpha n k, going up to alpha n n. So, when we measure the kth column, essentially this is the kth column, correct. Right. So, in here what is being done? The response DOF is varied, right, from 1 to n, okay, and the excitation DOF is fixed at kth DOF. So, this strategy in which the response DOF is varied and the excitation DOF is kept fixed is called a roving accelerometer test, because if let us say we are using one accelerometer to measure the response, then after measurement being completed at one point, we will have to move the accelerometer to the next point and then to the next point. So, this therefore strategy of FRF measurement or method of FRF measurement is referred as a roving accelerometer test. Later we will study that vibration shaker also can be used for excitation of the structure, and vibration shaker is a much more complex system than an impact hammer, and it is not easy to move it repeatedly from one measurement to another to shift the point of application of excitation, and that is why it is preferable to keep the excitation location fixed when a vibration shaker is used for application of the excitation. And that is why this roving accelerometer test is commonly used when a vibration shaker is used for model testing, right. So, this is generally used with vibration shaker, okay. So, another decision we need to make before FRFs can be measured is at what point the response transducer in a roving hammer test or force transducer in case of a roving accelerometer test should be located, right. So, the choice of response transducer and force transducer locations. So, if we talk of, let us say, a roving hammer test, right, then in this test we need to fix the accelerometer at a test point. So, that will be permanently mounted at that point and will not be moved or varied when the measurements are taken over different points. This location where, or the test point where this accelerometer is fixed, it should be such that all the modes in the frequency range of interest, which we want to measure, they should be observable from this location, right. So, all the modes should be observable from the location of the accelerometer, right. And the modes would be observable if the test point or the location of the accelerometer does not coincide with any of the nodes of any of the modes, right. If let us say if the accelerometer location coincides with one of the nodes of a particular mode, then that mode would not be basically seen in the response signal measured by the accelerometer, and then that mode cannot be then identified, right. And that is therefore the location should not coincide with any of the nodes of any of the modes. Similarly, in a roving accelerometer test, the excitation point is fixed, okay, and therefore here the all the modes should be excitable from this point, correct. And again the principle is that this location again should not coincide with any of the modes, any of the nodes of any of the modes, right. The excitation point is fixed, therefore the excitation point should not coincide with any of the nodes of any of the modes, okay. Another decision we need to make is about time and frequency domain parameters. So, choice of time and frequency domain parameters of measurement. So, earlier we have studied what are the time and frequency domain parameters and how they are related. So, what are the time and frequency domain parameters? So, one parameter is the frequency range of measurement, right, which is F max, correct. And then we have what are the number of samples in the time domain. Let us call it NT, number of samples in the time domain. Then we have the sampling frequency, which is we can represent by Fs, correct. Then we have the cutoff frequency of the anti-aliasing filter, correct. So, cutoff frequency of anti-aliasing filter, let us call it Fc. Then we have time resolution, or time step, that is delta t, right. Then we have the record length, which is t seconds, the length of the record. Then we have frequency resolution, right. What is the frequency resolution of the Fourier spectrum or the FRF? So, that is delta f, correct. And then we can also have the number of lines in the spectrum, which we can call as NF, right, because the spectrum is discrete. So, there would be discrete or finite number of lines there. So, you can see these are different parameters which are there, which describe the time and frequency domain. Now, we earlier studied in the signal processing that only 2 of these parameters can be independently chosen, while the rest of the parameters they get fixed, right. So, frequency range of measurement we already talked today, that how that can be decided, correct. So, the frequency range, let us say Fmax is fixed. The other parameter which often is provided in the FFT analyzer is choice of number of samples in the time domain, that is NT. So, that can be the second choice, and this NT is generally to be selected from a set of values which are expressed in the power of 2. So, therefore, we have selected Fmax, right, we have selected Fmax, we have selected NT, right. And now, how other parameters are get defined? So, the sampling frequency Fs, it depends on what is the frequency range of measurement. So, it is equal to 2.56 of Fmax, okay. And then we have the cutoff frequency Fc of the anti-aliasing filter, it is Fs by 2. Then we have time resolution delta t. So, this time resolution depends on the sampling frequency, that is 1 by Fs, right. And then we have record length t, that depends on the number of samples Nt into the time resolution delta t. Then we have the frequency resolution, that delta f is actually equal to 1 upon t, right, 1 upon the record length. And then we have the number of frequency lines, that depends on the range Fmax and delta f, correct. And Nf is also equal to, you can see it is also equal to Nt upon 2.56, right. So, these are therefore the relationships which relate the chosen parameters Fmax and Nt and all the other parameters describing the time and frequency domain. Here we have the factor 2.56 in the equation for sampling frequency, right. That is being taken, if you recall, the as per the Nyquist sampling theorem, the sampling frequency should be twice of the highest frequency limit, right, or the highest frequency component present in the signal, which in this case we expect it to be Fmax. And so, here the 2.56 factor is being taken in order to compensate for the non-ideal characteristics of the anti-aliasing filter, right. So, anti-aliasing filter does not have ideal characteristics where the all frequencies beyond Fc are completely truncated. So, that is why because the filter characteristics have some roll off, the frequency response does not have a sharp cutoff. In order to compensate for the roll off effect of the frequency response, this factor 2.56 is being taken. So, we also note from here is that if we want to improve the frequency resolution, right, that is delta f, then we must have a higher record length, and higher record length depends on the number of samples. So, if you take NT to be higher, then it will lead to higher record length and a higher better frequency resolution. So this is how parameter should be selected. So now let us talk about the calibration of the measurement system. So when we measure the FRF, we should know the correct values of the sensitivities of the force and the response transducers, right. What happens is that with continuous usage of these transducers, the sensitivities may undergo some change, right, and if the sensitivities are different, then what will happen, the FRF what we record will not be correct FRF, right, it will be scaled because of the errors in the sensitivity. And then it will lead to scaling errors in the mode shape. The mode shapes we get will not be accurately scaled, right. That is why the correct knowledge of the sensitivity of the transducer is required. To find the correct sensitivity, we may have to do calibration, and that may require transducer specific calibration, right. But for model testing, it is possible to calibrate the whole measurement system, okay. So that we get a calibration factor for the whole measurement system, and the FRFs we measure can be calibrated. So that is what we are going to now look at, that how to do the calibration of the whole measurement system, and that is often referred as ratio calibration. So in this, the idea is that we measure the FRF on a system for which we accurately know the FRF. Okay, and such a system is a heavy mass that is suspended and is made to oscillate like a pendulum, and then we measure the FRF on this system, and for this system the FRF can be accurately known, and then we can compare the measured FRF with the correct estimate of the FRF, and then from that we can determine the calibration factor. So what we do is that we take a mass like this, and then we suspend it like this, so now this mass would oscillate in a vertical plane, right, and then we can mount an accelerometer on this, like this, and then we can apply impact on this from this side. Okay, and then we measure the acceleration. So we can have, let us say, the FFT analyzer here like this. Okay, and then we have channel 1, channel 2, and then we can have signal conditioner or charge amplifier. So the accelerometer signal first goes to the signal conditioner, and then it goes to the one of the channels, and similarly we have the signal conditioner, and then we have the Hammer signal also going to into the FFT analyzer, and then this gives us the frequency response function like this. Okay, so let us say the mass of this pendulum is m. So if this pendulum or the mass is disturbed by small amplitude, then it can be approximated by a linear system, and it will behave like a single degree of freedom system, right. The frequency response function, the inertance for this single degree of freedom system, we know from theory that it is of this form. So, it looks like this. Okay. So, what we note is that this is the natural frequency of the pendulum, right. For the frequencies more than omega n, the inertance AT, right, T is for theoretical estimate of the inertance. So, AT is approximately equal to 1 upon m, okay, or maybe we can call effective mass, correct, because this effective mass can take into account the mass of the pendulum plus the mass of the extremometer, because that is also being attached to the mass. So, therefore, this the absolute value of this quantity, this is AT, right, and this is approximately equal to 1 upon m, okay, and therefore, because we know the mass of the pendulum and the mass of the extremometer, so we have a good estimate of this AT, and then what we do now, we perform the FRF measurement, right, using the setup as shown, and we obtained a measure the inertance. So, the inertance measured may look like this. Like this, right, and now this quantity, the absolute value of the inertance in the frequency range much above the natural frequency, let us call this AM, that is obtained by measurement, right, and therefore, now we can calculate the calibration factor, let us call that as CF, calibration factor. This can be written as AT upon AM, ratio of the estimate AT and AM. Now, AT and AM both are known, AT obtained from the theoretical estimate and AM being the measured estimate of the inertance in the frequency range omega much beyond omega n. And now what we can do? We can use this as a calibration factor to correct the FRFs we measure the model test, right. So, let us say if we measure the FRF during a model test, let us say we are performing it on a structure, let us say it is simple a beam structure, right. So, now we perform using this measurement system, the FRF measurement, and let us say the FRF being measured here is, let us call that FRF as say A, right, A of omega. So, this is the FRF that is measured. Now, we would correct this FRF using the calibration factor. So, then we can write this as say AC, that is the calibrated FRF, as A omega multiplied by the calibration factor. So, in this way we obtain a calibrated or corrected FRF. So, this calibration factor takes into account any changes in the sensitivity associated with the force transducer of the hammer, the response transducer, right, and any other scaling factors which might be there in the measurement system, right. So, all those factors are combined into a single calibration factor. Therefore, this method is quite effective in obtaining correct estimates of the measured FRF. So, in this way today we looked at test planning for FRF measurement, and we discussed the several decisions that need to be made related to the measurement, right. Now we can stop here. Thank you.